Hi guys, in this lecture we're going to look at isoparametric mapping. So let's just dive into this using an example problem. So we want to solve this differential equation here, and the difference from last time is that I'm adding a solution to this u here, and the load is 0, and also I have other boundary conditions here that are non-zero. So we'll see how to handle this. And this is really independent of the isoparametric mapping. I just like to change examples around, and so you see how you can handle all sorts of different equations this way. Just follow the recipe. We'll create the weak form here by multiplying both all terms with a test function and integrate, and then we will integrate by parts the stuff that is of higher order. And yeah, that's basically it. So if you do this, you will see that you will end up with this. The only difference really here is that we just deal with this u here, and it's just a multiplication with the test function and integration. So really nothing special compared to what you have done earlier. Alright, now for the approximation, we will use two linear elements, and we will insert this approximation into the weak form. So we'll follow Galerkin's method here, and we'll end up with this. One thing to note here is that, again, I'm using vector operations here. So this vector, the basis functions vector, is of course multiplying the solution vector, and this is the same as a sum. So it's the same thing. The same thing goes for here. So this is exactly the approximation. So I'm summing all the basis functions with all of the coefficients in U. Now, notice I have actually changed notation, and I need to do that. So I'm going to write it here. I'm changing notation from, well, what you have seen before is this vector notation here to this slightly other notation. Usually when I write on a whiteboard, I usually denote vectors like this anyway. The reason I'm changing this is that this thing, when I later need to do hat, it just looks very weird and it's laughable. So I'm gonna change it so it looks a little bit better. Yeah, so you just need to get used to this new notation style. Vector notations obviously should be done using bold script. It's just that Matlab doesn't handle bold symbols, at least yet, for Greek letters. That's why you need to have this workaround. So we have our approximation inserted into the weak form. Now we can break out the u here. So we break out u and we get this system formulation. Alright, so this thing here becomes a matrix, and this becomes a matrix as well. And if we just break out u, gather it, and combine these two integrals, we have two matrices here, S and M, multiplying u, and this is equal to g, because this here will be g. So let's talk about this more in parts. So we will have our stiffness matrix here, which we recognize since earlier, and we will have the mass matrix be this thing here. So wherever you see u, think mass matrix, because it will lead to that. Now I can go into why this is called the mass matrix. Really, it comes from weighting density, and if you look at it overall, it will become the mass of an object. So really, when you're doing dynamics, which we won't be doing, but when you're doing dynamics, you're using the mass matrix. It becomes very obvious, but that's just from a structural analysis point of view. In general, this thing is just has to do with the approximation of the actual solution here. So yeah, and it shows up in the L2 projection as well, and in several other places. But yeah, it's usually we call it the mass matrix. Now for the isoparametric map. So we will take a look at an example here. So the aim of the isoparametric map is to be able to efficiently integrate numerically. Alright, and I'll get to that in a second. So consider this a sample. We have this element stiffness matrix below. Now this integral here, I'll just paste this stuff in so we can take a look at it closer. So this integral here is in general hard, or at least very inefficient to integrate for this general range where x is in any points x1 and x2. So it would be easier if x was always in the range of 0 to 1, always and for every element. That way we can apply smart integration rules, as we shall see in the next lecture. But it doesn't really need to be just in this range 0 to 1. Actually, if you look at most lecture books, this range is actually -1 to 1. And the reason for that is that this integration rule sort of becomes symmetric, so you don't need to store so many points. But I'll get into details when we get to numerical integration, really. I never use -1 to 1 because it's easier to explain this going 0 to 1, because the integrals become easy. You don't need to deal with this negative lower bound, because if it's just 0 when you do it by hand, you don't need to think about it. So I prefer this way, really, but yeah, you can try it out either way. So we will define basis functions using this range 0 to 1, and they will always be able to be used in every element, and that's really the point here. So we can sort of predefine all of our basis function, and we never need to calculate them. And in the next lecture, when we talked about numerical integration, we will see that we really don't need to do any symbolic operations at all ever again. So yeah, so this parameter space of course here is going to be something else than x, because the real space is x. So we have our real space here. We have two nodes. We have this p and q node, or x and x1 and x2. And over here in the parameter space, we have our basis functions that are defined between 0 and 1 in this space called xi, Greek letter. So we need a map. We need to somehow to express x in terms of, in terms of xi. And the way we do that is by multiplying the coordinates x1 and x2 using the basis functions, which you recognize since earlier. They're just 1 minus xi and xi. The only thing you have been seeing is the difference you've been seeing is that it's actually 1 minus x and x. That's what you have been working with. But now we just change the variable to xi, and suddenly we have a fixed basis function which never changes. And that's the beauty with it. All right. Now I haven't really in this graph here denoted phi with a hat, but usually that's what I do. But I sometimes use this interchangeably, and I'm sorry for that. I should really be consistent about notation styles. But yeah, we shall see soon that these basis functions really are the same. If you evaluate them using the map, they're really the same. So the notation style really doesn't matter, because we will never be using general basis functions using x. Really, we'll just always be using the isoparametric mapping. So now this is a bunch of text. I'm just pasting it in so you can view this later and read it and use it as a lecture book or whatever. So using the parametric mapping, we can switch from the general coordinates x1 and x2 to 0 to 1 always for every element. And the advantages are that the basis functions are the same everywhere, and we can utilize numerical integration to compute the integrals. And we will look at that in the next lecture. But this makes the computations efficient and straightforward compared to the previous approach, in which we had to do everything sort of symbolically, right? The differentiation needed to be done symbolically, and yeah. So for each element, we had unique basis functions, and that was a problem. Different basis functions everywhere, and the different derivatives of these basis functions as well. Also, we needed to integrate that symbolically. So now using this numerical method, which we will get into very soon, we will actually save lots of time. The speed up is going to be orders of magnitude faster than any symbolic computations we've done. And that's how horribly inefficient symbolic computations are. So for industrial size problems, this is a must. We have to use the best method in order to decrease every second of computation time. And right now we're dealing with very small problems. We're dealing with what, 10, 20 elements, something like that, and they are 1D, and we have only 1 degree of freedom. So basically we're dealing with like 10, 20 degrees of freedom. In energy you have millions of degrees of freedom, and these matrices are huge, so everything needs to be thought about and optimized. So using these linear elements, we can draw this graph here. It's always nice to have a mesh written out like this. So we have our two linear elements, we have our nodes here, 1, 2, and 3, and we have the coordinates x1, x2, x3 here. We have the local coordinates x1, x2 for every element. They're going to be the same as we have seen in the previous video. And now we will apply our parametric map. So this thing here, where all basis functions are denoted with this hat, and they're always the same because they're defined in this xi space here, going from 0 to 1 all the time. Both of these are going to be applied on both elements. We can define the map from the parametric space to the real space using the basis functions. For linear elements, where xi is in 0 to 1, our basis function is, well, what it was when in the first lecture we ever did, basically. It's the same thing. It's just that we call this, we denote this function with hat to denote that this guy belongs to the parametric space, and also its variable xc. That's why I sometimes skip the hat, because, you know, if I see xc, I know, alright, parametric space. If I see x, I know, okay, real world. So x defined on the interval x1 and x2 is given by this linear combination here. So we have our basis functions of xi multiplying our coordinates. Alright, and this is equal to, so this becomes, if you multiply it in, we have our 1 minus xi multiplying x1 plus xi multiplying x2. If we do this operation, we can see that we have, okay, we have x1, and then we're just linearly interpolating this range x2 minus x1 using xi. So really nothing special. What happens now if we insert xi equal to 0 and xi equal to 1? So we can see when xi is equal to 0 here, we just end up with x is equal to x1, and when xi is equal to 1, we end up with x is equal to x2, exactly what we want. So if we throw this back into our basis function here, into the original basis function here, we can see that it turns out that these both basis functions are really the same. So they're producing the same stuff, because we get x back, we get x1 back, and we get x2 back if we use the map. Right, but we also need the derivative. We need the phi dx. So we can get that using the chain rule. So using the chain rule, we sort of break this apart into pieces. We get the phi hat xi multiplying xi dx. Right, so the phi hat xi is straightforward. You just take this derivative here, you get what, minus 1 and 1, so that's straightforward. But what about xi dx? Well, the inverse is easy. We can do dx xi. So we take our x here, we take this derivative, and we end up with x2 minus x1. And this is actually defined as h. So h is our element size. But really what this also is delta x. So it's the difference of x, which is our element size. In 1D, this is the mesh or element size, but this is also known as the Jacobian. And actually the Jacobian is a matrix. Since in 2D and 3D it becomes a matrix, which we will see in future lectures. Alright, so we get that the phi I dx is equal to the phi hat I dxi multiplying dxi dx here, and dxi dx is of course 1 over h, because we can just take the inverse of that. And it's also known as this inverse of the Jacobian. Now note that we can also derive dx. So we can take dx, dxi, start out with that, and say, right, this is h, and then we can just multiply dxi up to the right hand side, and we get dx is equal to h dxi. And that's how we make this variable change in our integral. So this will be useful for integration when we get to it. And generally, dx dx can be computed using dx dx. It's summation of the derivatives of the basis functions multiplying the coordinates of the mesh. So apparently this is easily computed since it only depends on the element coordinates xe, and yeah, the phi dx is pre-computed ahead of time. It doesn't depend on the elements. Alright, now we can formulate the weak expression in the parametric domain. So we start off with our standard integral, which we had from the weak form here, and we just identify this right hand side here as the g vector. So I hope you can see that this is underscored. Using isoparametric mapping, and we can really write it here that this is using isoparametric. So using isoparametric mapping, we arrive at our new weak form, where all of these differentials here now are expressed in terms of the parametric basis functions. So we're of course multiplying them by 1 over h here, since this is exactly what we have here. So we're replacing this with this here, and then here again, and then this is multiplied by h times dx, because h times dx is dx. So this whole integral here changes from 1 to 2 dx to 0 to 1 dx. And we can simplify this in the next step. So since this 1 over h times h, one of these gets cancelled, we only have one left. So we have our d phi dx, not dx. So we have our d phi dx transpose times d phi dx, and then times 1 over h times dx. So one of these 1 over h times h gets of course cancelled. And over here in the mass matrix part, we have d phi times h dx. Alright, now we will actually do this by hand. So we have two elements, and we will insert our parametric mapping into both of these. So we will see that we can use the same basis functions in all elements, and the only thing that will change is the mesh size. We will show that now. This means that almost everything can be pre-computed outside of the main for loop for efficiency. So we don't need to calculate everything every time. For element 1, we have that x1 is equal to 1 here, and x2 is equal to 1.5. So we're in element 1. This is our element 1 to 1.5. Our basis function is always the same. So we have our basis function, it's 1 minus c and xc, and its derivative is of course minus 1 and 1. So you can just take the derivative here, and you'll see that this is this, and this is independent of the elements. Okay, then we take dx dx here, and we see that this is d phi dx multiplying xc, and this becomes minus 1 and 1. So that's our derivative, multiplying x1 and x2, and this is of course nothing but the difference, which is again the Jacobian in one dimension, and it's also what we the notation we use here, h, which means mesh size. Alright, so we just recap what we have. So we have h is the difference in, or the mesh size, x2 minus x1. We have that dx is h times dx, and dx is equal to 1. So dx is equal to 1. Well, that means that our range here, the size of this parametric space, is 1. The area, if you want, because in 2D this will actually become an area. And if we were to use something else than the space 0 to 1, if we used the classical, which is minus 1 to 1, then dx, this range, this integral, would be 2. So we would need to take that into account here. But currently, we just keep it. So this is really simpler to handle. Alright, then we have our basis function, the derivative of the basis function here. And this is taken from above. Now we will see what this becomes with actual numbers. Minus 1 and 1, derivative of the basis functions, multiplying 1 over h here. Right, now we have everything, and we can just plug it into our matrices here. So we will do that next. So our element stiffness matrix here for element number 1 is the integral 1 to 1.5, and then we have our basis functions here, the derivative with respect to x. And now we can rewrite this using the iso-parametric map, and this becomes the integral from 0 to 1, and our basis functions are, I'm just keeping them dependent on x here, so they're still the same, but now I'm just changing the x here to h1 times the c. And in the next step, I will actually do the complete conversion. So we have the integral from 0 to 1, and then we have replaced d phi dx here with d phi dx transposed 1 over h1 times the other one, d phi dx 1 over h1 times h1. Now this simplifies to the integral here with the basis functions multiplying each other in this way such that they will actually form a matrix. So let's put it in real numbers. So we have the first integral, we have this integral from 0 to 1, we have our basis functions, the derivatives, and these are transposed. They look like this. It's a 2 by 1, and the other one here, it's a 1 by 2, and we can see that the operation mathematically makes sense, and we will end up with a 2 by 2 matrix. So do that operation, and you will end up with this. So we have minus 1 times minus 1, which is 1. Then we have minus 1 times 1, that's minus 2. And then we have 1 times minus 1 here, and 1 times 1 here. That's that operation. And we can simplify it even further. We can do the integration, and now this integration is very straightforward. You just replace this with xc and insert 1 here, so it's the same stuff back. So that's why it's easier than if we had this negative 1 to handle as well, at least by hand. So yeah, we end up with this, and 1 over h1 is of course 1 over x2 minus x1. We shall now take a look at the element mass matrix for element 1. So the element mass matrix for element 1 is the integral of going from 1 to 1.5, and we have our basis functions here, and we're going to replace these with the iso-parametric map. And again, we're going to take this in steps. So using the iso-parametric map, we have this integral change from 0 to 1 instead, and the stuff is the same, times h1 dx. Okay, now we need to change this for this to make sense. So this is the same as the integral. Now we evaluate these basis functions here, and they're 1 minus c and xc, and then 1 minus xc and xc. You will see if you do this operation here, we will end up with this quadratic thing, 1 minus 2xc plus xc squared. That's because we're multiplying 1 minus xc with 1 minus xc here. So we will have quadratic elements everywhere. So this integral here is now quadratic instead of being like in this case here, it is constant. Alright, if you do this integration, and it's pretty straightforward, you will end up with this integral, or this matrix 1/3, 1/6, 1/6, 1/3 times h1, and this of course gets expanded to this here, x2 minus x1. Alright, so that's the job you need to do in order to apply the iso-parametric mapping by hand. And as you've seen, it's not that much work really, especially since we get into this now. So for element 2, we have of course a different x1 and x2. So what happens there? Well, the only thing that changes is h here. So h2 is going to be x2 minus x1, which is 1/2, and really that's the same as our previous h1. Why? Well, we have made our mesh ourselves. So we have said that, alright, this thing here is linearly spaced. So h is always going to be the same everywhere. And that's kind of nice because we end up with the same matrices. So every matrix, as long as our mesh has the same length, all of these stiffness matrices and mass matrices are going to be the same. And that's really not the strength of the finite element method, because as we will see when we do the assembly shortly, this method that we're using here now will yield the same sort of matrices as the finite difference method, but the finite difference method can be created in a much more efficient way than what we're doing here. So the strength with the finite element method really is that H can change. It can be any size, really. And in the finite difference method, that's usually not the case. You usually have the same range everywhere. And you have, in 2D, you have a conformed mesh. So you cannot have an unstructured grid. You have a conformed grid. It's like a checkerboard. Every element has the same sort of size, and even if they're sort of maybe locally somewhere a little bit, you have more lines locally somewhere, you cannot have a different shape. So they all have to have the same shape. It's a grid pattern, and for finite elements we can arrange our triangles and our quadrilaterals in any shape and in any size. Of course, there are limits to that. You cannot squish tetrahedrals or triangles as much as you want. The derivatives will all get messed up, but usually you have algorithms that handle that. But yeah, so the thing is that the strength of the finite element method is the unstructured nature of the mesh compared to the finite difference method, for instance. Alright, now we are at the assembly process. So these matrices need to be assembled. So we have 2 of them. We might as well have 20,000 of them. How do we do this? Well, the assembly process, as explained earlier, we're going to start out with that. So we have this drawing will help us understand what we're doing now. So our global stiffness matrix is of course a 3 by 3 matrix, because we have 1 degrees of freedom and we have 3 degrees of freedom in total, so 3 by 3. And the first element, element stiffness matrix here, it's a 2 by 2 thing, and it will be placed at these locations here, governed by these local degree of freedom. So there are 1, 2, and 1, 2. So at that place, we're going to place the other one. And we are assembling. That means that we are taking whatever exists there, and we're adding on top of that. So here, we're taking whatever exists there, and we're adding on top of that. So for the next one here, 2, 3, we will see an overlap here at 2, 2. And that is going to be handled. Now let's take a look at that. So we have our first element placed into this stiffness matrix here at the positions 1, 2, and 1, 2. So that's here, and this leads to in the second line here we're adding. So S2 here is being added to the positions 2 and 3, which is here, and there's an overlap in the middle node here, of course, because we have the contribution 2, 2 from element 1 and the contribution 1, 1 from element 2. And this is the same process we're going to do for the mass matrix. Now, since we have, take a look at the numbers, since our element stiffness matrix is of this form here, we have 1 minus 1 minus 1 1 over hi. So the only thing that is changing is h. We will take a look at how that looks assembled. So this is our assembled mass matrix with 1 over h broken out. Now if we insert h into this matrix and look at what it becomes totally, you can see here that this is what we end up with. And with the mass matrix, it's the same thing. So we have our element mass matrix here on this form for linear elements, So actually this guy is the same for really any element, as long as it is linear, and as long as we are solving this particular problem, really. So I mean, we could modify this. So if let's just quickly mention that if we had some constant, let's call it a here and b here, then b, then these constants will affect our solution as well. So we would have a here, and we would have b here in our weak form. And this will all propagate down to a constant being here. We would have, let's do it like this. We would have a here, and we would really have, well, a here as well, and b here. So that's what would happen. So it's in a sense dependent on which problem we're solving, if it's on this form that I've showed you here. But in general, these are not the only differential equations we can solve using this method. So if we have something else here, which is, I don't know, third order, fourth order, then of course these matrices will not look the same anymore. So just keep that in mind. So that's why I usually don't like to say like, yeah, in general this is always the same. No, it's depending on which differential equations you're solving, of course. But now inserting these the values here, we will end up with this symmetric matrix. So I just don't write out this other part here because it's the same as this one. So just mirror it down there. And we have h in front of this, which becomes, with h, we end up with the final mass matrix here. And we're done. So we have our mass matrix, we have our stiffness matrix, and we can move on to boundary conditions. So these are our boundary conditions. We have our mesh. It's always good to have this picture again. I cannot overstate this. I want to see this picture in every report, because if you just jump head first into solving stuff in Matlab, you will just make a mistake and you will ask me, and then I will just tell you to create this picture, because you will realize your mistake very quickly if you have this in front of you. So we have the boundary conditions. du1 times this test function at 1, never mind that business, but yeah, so this thing here is going to be denoted g1, and then on the other hand, on the far end side here, we have du dx of 2, which is going to be g2. Alright, you can take a look at this more closely. So this thing will be expanded to this, right? And note now again this negative sign here, please don't miss that. So we can write what we have. We have that the du dx of 1, this boundary condition here, is equal to 2. That means that g1 is equal to minus 2. So this minus sign is always in front of the value, and the value in this case is minus 2. And I've chosen this carefully just to show you that this can happen, and you need to be careful with this. Alright, then for our actual solution, so the boundary condition at 2 is equal to 1, so that means that u3, the third degree of freedom here, is going to be 1. We need to combine the stiffness and mass matrices into one system matrix to be able to handle the boundary conditions more easily. So I'm just going to do this non-mathematical operation here. This is a programming. This is very valid in programming, but it's like every mathematician will scream at you, well, what's happening here? What are you doing? But yeah, programmers will understand that we are overwriting s here with s plus m. Okay, we need to talk about modifying the right-hand side. So I've drawn this picture from the PDF lecture notes. We have our system matrix here. So this is the combination of both S and M. Come on. And we have our solution vector here, and we have our right-hand side here, this black stuff. Now, U3 is known. And yeah, it was known in the last lecture as well, and we didn't do this business. Why not? Yeah, because U3 in the previous lecture was actually 0. Now it's not. Now U3 is actually 1. So that means we have a solution that is known here, And this will, if you think about it, if you take this physical analogy with having a spring. So you're holding a spring in your hand, the right hand end of the spring, you're pulling 1 millimeter, let's say. And this thing, this sort of prescribed displacement that you're doing will of course lead to a force in the spring. And this force we call a reaction force. And that's the same thing happening here. So this U3 here multiplied by this column will really create a force, a reaction force. And we need to take that into account systematically here. So that's what we're doing. We're multiplying U3 with, because if you look at it here, what is this going to yield? It's going to yield the right hand side. So this stuff here, S11 multiplying U1 plus S12 multiplying U2 plus S13 multiplying U3, that's actually a reaction force. It's a force on the other hand. And this stuff here is going to cause a reaction force that we need to take care of. So what we're going to do is we take all of this stuff, which is going to multiply U3, and we move it to this side here. So we're just going to take minus, because, well, we're moving it here, so it's from positive to minus. And we're putting it in here as a reaction force. So since U3 is known and not 0, because last time it was 0 and it didn't really affect, it was just a reaction force of 0, so it doesn't affect the system. In this case, it will affect the system. So it is not 0, it will affect the system, and it's acting as a reaction force, and it needs to be treated as such. So we will take it, we will move it to this right hand side. The whole column will be multiplied. So, and the whole column we're choosing here is the one that is going to multiply U3 again. So it's the column which has these 3's here. So depending on if we knew U2, then we would be taking this column, and if we knew U1, we will be taking the first column. So that column that is corresponding to the degree of freedom is going to be moved to the left hand side. Okay, so we start off with our system equation like so. We have moved this stuff over to this side here. Now what do we do? So we have modified the right hand side, and let me just put this thing here. I want it to be known that this is important. Now we need to reduce the system, so we are going to reduce the system, and this is also an important step in assembly. So reducing the system means basically we're looking at, all right, what is known? Well, U3 is known. All right, so all of these, this whole equation here that has to do with U3 and this column is going to be just thrown away. We don't need it. That's not going to be our solution system of equation, or our system of equation to be solved. Yeah, it is there. This stuff is still valid. It's going to cause a reaction force and everything, but we don't need that stuff. We need to solve this here. This little matrix multiplying U1 and U2 is going to be equal to minus G0, and of course this stuff here. So there's still something that is affecting this right hand side, which needs to be there. But everything that has to do with U3 is known, so we don't need to take care of it. In fact, we can't have it there. The system is going to be overdefined, and we're going to end up with this error message with the system being ill-conditioned. So we are reducing the system by removing equations where U is known. The 3 degrees of freedom are thus 1 and 2. And our equation system becomes finally this here. So we have 2 unknowns and we have 2 equations, and we can solve this problem. And the solution might look something like this, the final operation. Alright, so that's basically the lecture. Now I'm going to go over and implement this in Matlab as a tutorial. So I urge you to do this by hand before going into Matlab code. So this is the business we have. We have n is equal to 2. Those are a number of elements. We have the same business with the x node and nodes, and the length of the number of nodes and the number of equations. And we have our stiffness matrix, and now we're adding the mass matrix, but it's going to be the same size as S, so we just call it that. We don't really have this, so I'm just going to remove that. And what we need to do now is we're still doing a little bit symbolics here because we haven't gone into numerical integration. So we need our symbolic xi here, but now we're defining this outside of the for loop because this is always going to be the same. So phi here is 1 minus xi and xi, and then we can actually get into our for loop. For IEL is equal to 1 to n, and we're going to populate this with a bunch of stuff since before. So we're just copying stuff in, and now the new stuff. So we can call our mesh size just x2 minus x1. So this is the complete size of the so I'm just gonna write mesh size here. That's the size of the element. No, element size, sorry. All right, now for the element stiffness matrix. Well, we can again go back and just remind ourselves how this looks like here. So this operation, this is what we're doing here. So we have this integral going from 0 to 1, and it's varying with xi now, and we need to take the derivative of the basis functions, transpose times itself, but not transposed, times 1 over h1. So that means that we're doing the phi, and we're transposing it, and we're multiplying it with itself. So if we just run this, we can see what's happening here. Alright, so we have this matrix, good. Now we're multiplying that with 1 over h, like so, and we need to integrate this. So we haven't talked about numerical integration. That means that we need to do this, unfortunately, using int still. And it's going to vary with xi from 0 to 1. So this is what we're doing. And because this stuff is just, well, 1 over h, then this whole thing will just be the same as the input. So it's not really changing anything. But yeah, in general, we need to integrate this. All right. How about ME? Well, ME is going to be phi, or phi, transposed multiplied by phi. And now you can see here that, alright, so let's just do this transpose business this way so we don't get this conjugate thing. So we have this quadratic thing, okay? And if we multiply this with h, then we know we get h in there, and then we need to integrate this from 0 from, but with respect to xi, from 0 to 1, like so. And you recognize this output is the same stuff we had above, and you see here also that for both of our elements, these two matrices are the same. All right, now we just assemble this. So we have S inodes and inodes, same as S of inodes and inodes, and we're adding SE to this, and the same goes with, I can really do it this way so you can show the output. I'm lazy, I'm gonna copy this and just change M here, here, and here. And I'm gonna run this, and inodos, it's not there, inodes, indos, indos, inodes, indos, indos. Need to fix this, indos. There's no such thing. And there we go. So we could really, if you want to compare your results to the stuff above, you can change, you can do sim m here, and you get this on this format here. So it's comparable to what we did by hand up here. And you can see that it's the same. Okay, so now once we have done this, we are combining our system matrix. So we do S is equal to S plus M here. So we have our combined system matrix, and we can finally start applying boundary conditions. So I'm just going to copy stuff in here. So boundary conditions, this is what we have. So now we can start. So we have all nodes, same way as we did before. These are all of our nodes. Just take a look at it. This is what we have. And then we have our prescribed view, the actual node which is prescribed is the last one here, so that's number 3 then. And then we create our solution vector with all zeros, and we set the prescribed one using this way. So that this is what we didn't do last time, but now we're setting this, so this is actually 1 here according to here, to what we have here. All right, and then we're just finding out which degrees of freedom are free using the setDiff operator. And we are creating G, the G vector here, just a bunch of zeros, and we are setting the first one. We are setting the first one, G of 1. The first one is being set to -2. Be careful with this. So this will become positive, like so. Now we need to modify the right hand side. So modify the right hand side. So how do we do this? Well, we're going to take S, and we're going to take all the rows and the prescribed column. So presc U underscore U. So this one here. So if you look at which one this is this one here. See the 0 on top. So we're taking that one. So we're taking all rows and this column, which is the third one, and we're multiplying that with its with the corresponding solution. And this is beautiful because really what we're doing here works even if we had more nodes prescribed. So of course for this problem it doesn't really make sense, but in 2D you can have geometry, and you can have several nodes on this geometry being locked to the wall, so you know that they are immovable, they're not moving. And then this thing, when you're moving stuff to the right hand side, or yeah, in that case it's 0, but yeah, you can have a plate, and then you can have one side of the plate that means several nodes, maybe tens or even hundreds of nodes can be known what they are, because you're prescribing, saying, okay, move this 1 millimeter away, or -1 millimeter away. So this really becomes a vector, and this whole thing here becomes a matrix operation, but it's the same process. It's actually exactly the same code. The only thing we're changing is here. But yeah, we're not going to do that. You're not going to do that, but I'm just saying that this code here is just you just move it to 2D, and you have a solution there as well. All right, so this is our right hand side. Now we need to define what our right hand side is. So F here denotes right hand side, and we have G minus this stuff here. And again, we take a look what we have here, and that's exactly that. We have G minus this S times U business. So exactly this. And if we run this, we can actually see our here that we are getting reaction forces. So it's not affecting the first one here. That's still just 2, but the other ones we're definitely getting reaction forces here, or reaction forces. They are not really reaction forces, but yeah, you can think of them that way. All right. So once this is done, we can solve for the degrees of freedom. So we do that exactly the same way we've done in the previous lecture, and we get our solution. And again, we have no idea if this is true or not. Well, the only thing we can see is that it's respecting the boundary condition here we have, which is U3 is equal to 1. But other than that, we have no idea. So we need to visualize this solution. So we will visualize our solution here from 1 to 2. So I'm going to plot the true solution here. There we have that. And then we can do the standard stuff. Hold on and plot. And we're plotting our x coordinates and our y coordinates, u, and we are doing this with markers and straight lines connecting these, and this is going to be blue. And bam, we have our solution, and it looks okay. Now let's play around with this. That's the fun stuff. So what happens if we mess stuff up? I just want you to see that. So you forget this negative sign. Boom, completely different solution. Just this minor thing here can mess up the solution so much. How about you forget to modify the right hand side here? Then f is equal to g, and you get this. So it's sort of, it's just taking this into account, but it's really shifting the whole solution in a direction here. So those are the typical mistakes that you can make, and yeah, you can play around with this and add more stuff. So this is the first example. Now that we know the theory, I will actually show you a different example in a different video where we can modify this thing here to be something else. So we have stuff to explore. What happens if we have 1 here? What happens if we have 2x here? What happens if this is a polynomial of some order or whatever? Yeah, and also we can change this stuff around and as well. So yeah, you will be wise to practice changing of this second order differential equation and play around with different boundary values. They don't need to be this all the time. You can actually have 2 force boundary values. You can have 2, yeah, so you can have 2 so really we should talk about this. I haven't talked about the naming convention for boundary values, but mathematically they're mathematical names. I've just called these sort of the solution boundary value and the force boundary value, but really they have names. This here is called the Neumann boundary value after a German mathematician, and this guy here is called the Dirichlet boundary value. Don't ask me why famous mathematicians are always German or French, but that's statistically true. So yeah, so we have Neumann and we have Dirichlet boundary conditions, and if you're searching online for the finite element method, this is what you will see all the time. So yeah, I'm putting it to you that this is what it's called, and not just in the finite element method. It's the same thing for really anything that has to do with solving equations. You have Neumann solving differential equations with boundary values. At least you have Neumann and you have Dirichlet boundary conditions. So for the second order differential equation like this, you could have 2 Dirichlet boundary conditions. That's 2 conditions on this type. So we would have u1 is equal to something here, and we could solve that easily. And we can have 2 force boundary conditions as well, or 2 Neumann boundary conditions. But that's more tricky because if u doesn't exist here, you basically have a unlimited amount of solutions. You can actually do this stuff in SolidWorks. You can take a plate and you can just pull it apart by putting 2 forces, 1 on each side, and not applying any fixtures on it. And that thing, there's no solution because you have unlimited solutions, because this whole thing, this whole plate in space can be in any y position, xy position, and it's still true. The solution is still true. So yeah, it's basically there's nothing locking it into one exact solution, one true solution. So that's why this is a little bit dangerous, but it sort of works when u is set to something because this stabilizes it. But yeah, now we're just talking about mathematical theory here, really outside of any applications or anything like that. But there's analogy to physics, though, still some. So yeah, you can play around with that, and I will actually make some more videos on examples of this without all of the theory involved. Good. Now, in next lecture, numerical integration. See you then. Bye.